Welcome back to Hansen Theory. If episode 1 changed how you think about solubility, today's episode will change how you see molecules themselves. Because coatings do not fail randomly. They fail because molecular forces are either aligned or fighting each other. Most engineers talk about chemistry. Very few engineers understand interaction physics. And that difference separates formulation operators from formulation thinkers. Let us start with a hard truth. When you pour a solvent into a resin solution, nothing magical happens. There is no invisible dissolving process. There are only molecules interacting with other molecules. Attraction, repulsion, alignment, mismatch. Everything you see at the macroscopic level, clarity, haze, viscosity, dispersion, stability, is a result of microscopic forces. Hansen theory simplified this complexity into 3 dominant interaction categories. Not because only 3 exist, but because these 3 explain most coating behavior with engineering-level accuracy. The first force is dispersion interaction. This is the most misunderstood force in coatings. Dispersion forces exist in every molecule, even in nonpolar hydrocarbons, even in so-called inert solvents. They originate from temporary electron cloud fluctuations. Molecules momentarily create small dipoles. These dipoles attract neighboring molecules. It sounds weak, but collectively, dispersion forces are powerful. They control how hydrocarbons dissolve polymers. They dominate solvent behavior in aliphatic and aromatic systems. They influence viscosity, flow, and leveling. In many resin systems, dispersion forces provide the base compatibility, but they rarely solve everything alone. That is where the second force comes in. Polar interactions. This force appears when molecules have permanent dipoles, meaning one side of the molecule carries partial positive charge, and the other side carries partial negative charge. These dipoles attract each other like tiny magnets. Polar interactions become critical when working with esters, ketones, nitriles, acrylics, epoxies, and functional polymers. This force directly influences adhesion behavior, resin compatibility, additive performance, and solvent strength. Many formulation problems happen because engineers underestimate polarity mismatch. They select solvents with strong dispersion compatibility, but weak polar interaction matching. The result? Partial dissolution, cloudiness, instability. Then comes the third force, hydrogen bonding. This is the most selective and most powerful interaction in coatings chemistry. Hydrogen bonding occurs when hydrogen attached to electronegative atoms, like oxygen or nitrogen, interacts strongly with other polar groups. This force controls urethane compatibility, alcohol behavior, water sensitivity, dispersant performance, and pigment wetting. It is also the force that creates many stability problems when mismanaged. Too much hydrogen bonding mismatch creates phase separation. Too little creates pore wetting and dispersion. This is why waterborne systems are far more sensitive than solvent-borne ones. Hydrogen bonding dominates aqueous chemistry. Now here is where minority thinking begins. Most engineers treat these 3 forces separately. They think, this solvent is polar. This resin is hydrogen bonding. This additive is dispersive. But real formulations never operate in isolation. All 3 forces act simultaneously, every second. In every drop of coating material, your formulation is not controlled by one interaction. It is controlled by the balance between all 3. This balance determines whether your resin dissolves smoothly, whether your pigments wet properly, whether your film remains stable over time. This is why copying formulations without understanding force balance is dangerous. You may replicate ingredients, but you will never replicate interaction behavior. Now, let's expose another industry mistake. Many engineers assume that stronger forces are always better. This is wrong. Excessive hydrogen bonding can increase viscosity. Excessive polarity can reduce flow. Excessive dispersion dominance can weaken adhesion. Engineering is not about maximizing forces. It is about balancing them. This is what Hansen theory truly teaches. Not numbers, not charts, not software outputs. Balance. When you understand dispersion, polarity, and hydrogen bonding as physical interactions, not abstract parameters, your formulation logic changes. You stop asking, which solvent dissolves this resin? You start asking, which combination of forces produces the most stable molecular environment? That shift alone separates average formulators from high-level engineers. Now here is something most textbooks will not tell you. These three forces are not equal in importance for every system. Automotive clear coats behave differently than industrial primers. Waterborne systems behave differently than solvent-borne systems. High solids coatings behave differently than low viscosity coatings. Your job as an engineer is not to memorize values. It is to understand which force dominates your system and which force is limiting your performance. Once you identify that, troubleshooting becomes logical instead of experimental. You stop randomly changing ingredients. You start correcting molecular mismatches. This is why senior formulators can solve problems faster, not because they know more products, but because they understand interaction behavior. In the next episode, we will move from forces to geometry. We will explore Hansen space, not as a mathematical model, but as a visual representation of molecular compatibility. You will see how these three forces become coordinates, and how distance becomes prediction. If you want to move beyond trial and error formulation and start engineering coating behavior, continue with the series. This is Hansen theory.